in Lecce, and he is researching patient process and patterning recognition at the computer engineering course of the University of Salento. His main research interests are in the field of computer vision and pattern recognition, applied to audio measurement, security, and surveillance, robotics, medical imaging, and manufacturing. Nimo?
Yes, do you hear me?
Yes, yes. Benvenuto.
Grazie. Thank you, Douglas, for the nice introduction. And good morning, everyone. My apologies for not being there, but fortunately, I got injured and I couldn't travel. But anyway, I am going to talk about the research activity we are doing at the Institute of Applied Sciences and Intelligent Systems of the National Research Council of Italy from the computer vision point of view. Just a quick introduction about us. The Institute of Applied Sciences and Intelligent Systems was founded by Professor Caianiello, which was one of the pioneer AI, artificial intelligence pioneer in Italy. And he founded the cybernetic laboratory that then became, at the end of the 70s, the Institute of Cybernetics. So it's one of the institute of the 103 institute of the Italian National Research Council of Italy, which is the biggest research organization. And then in 2015, we changed the name just to be much more actual in the Institute of Applied Sciences and Intelligent Systems. And the headquarters is in Pozzuoli, near Naples. And in 2015, we founded the Lecce unit. Here is, let me take the pointer. Oops. I'm trying to select the pointer, but okay. Anyway, do you see the mouse eventually? Okay. So here we are in the university campus, the University of Salento campus, where there are where we are in the high technology district as a location. So just let us jump into the talk. We know that computer vision has a rich history that has spanned for the decade of efforts to enable a computer to perceive visual stimuli meaningfully. So machine perception spans from several levels, from low-level tasks to, such as identifying edges, to high-level tasks such as understanding the complete scene. And we have had a very big jump in the performance, resolving very complex tasks due to the maturation of the deep learning, which is a type of machine learning that enables end-to-end learning of very complex functions from raw data, strides in localized computer power through the graphical processing units, and above all, the open sourcing of large level data set that we use to train our model. If the model is mainly supervised. So the problem that we usually try to solve are essentially supervised. That means that we need to have the data with the associated class to which we would like to recognize. And this is a very critical aspect in the sector of medical imaging, because the annotator must be an expert. And usually the expert, the medical doctors, they don't have time to annotate the data, especially for images. And as we know, deep learning is usually used in a fine-tuning way. That means that we grab from the net architectures that have been trained on well-known datasets like ImageNet for the classification or COCO for object detection and so on. And now in medical imaging, there is also the application of deep learning to generate synthetic data, which is useful to, for example, augment a data set. But recently, self-supervised learning, in which implicit labels are extracted from data points and used to train the algorithm, for example, in non-medical imaging context, for ImageNet images, for example, the task was to predict spatial arrangement of tiles generated from splitting an image into pieces. So self-supervised learning has pushed the field towards fully unsupervised learning. And applying these techniques in medicine will reduce the barrier for the development of new model or the barrier to solve a very complex task where many data are needed and we don't have the possibility to grab this data. If we think to computer vision in medical imagery, let's think about static medical imagery. So we can divide the sector in four applications: radiology, pathology, ophthalmology, and dermatology, which are mostly the sectors that we have been working with. And in recent years, there have been a very boost of publications in this context, as for example in dermatology, because we have seen that the application of deep learning techniques may improve the quality of the diagnosis, especially in dermatology, as a paper from Nature have been proved. And we will talk about the radiology sector, and in particular fighting COVID-19 from X-ray and CT-scan, both in 2D and in 3D. As we know, COVID-19 is an infectious disease caused by severe acute respiratory syndrome, coronavirus 2. And its name is due to 70% compatibility of its genetic sequence with that of SARS-CoV, also called the SARS. And as we know, the first case was registered in 2019 in Wuhan. And at the beginning of 2020, we started working on in this context. As if we see a taxonomy of the lung disease, we can see that there are mainly pleural effusion, lung opacity, and pneumothorax. Then from lung opacity, we have other pathologies, other disease. And what we have done is to try to solve the complex task of classifying COVID-19, considering the fact that COVID-19 can be confused with other disease, like, for example, if we consider the viral can be divided in varicella, HSV, and so on, coronavirus, where coronavirus is SARS, MERS, and COVID-19. So it's a little bit complex task to detect the COVID-19 and separating from the others in the viral subgroup. We also worked by considering the lung opacity and the bacterial. Now we will see in a few slides the data set that we have proposed. So as we know, the definitive diagnosis is the RT-PCR, the gold standard, which has several false negative, and it's the process is time consuming. It's very long. Applying X-ray or CT scan may make very fast test, and we wanted to study the application of these acquisitions techniques in order to see if we can have an efficient AI system that may substitute the RT-PCR and also may follow the disease. For example, for the CT scan, it is possible to understand the severity or the follow-up of the infection. So at that time, the number, when we started working on it, the number of X-ray scans were very, very small. And the studies that were published were not unified. We just made a survey at the time of the research activities that have been done for detecting COVID-19. The majority of researchers applied their own data set without sharing it, and the problem was to distinguish COVID-19 as a binary problem, COVID or non-COVID, or with 3 classes or 4 classes, like, for example, COVID-19, viral, bacterial, and the normal class. So what we did is to propose a data set with a baseline architecture, the results of the baseline architecture, the convolutional neural network that we introduced were the ResNext 50, the Inception V3 and the DenseNet 161. We use the focal losses loss function, the other optimized, and we published this on sensors. And we introduced 2 different data sets that we made publicly available. One related to 3 classes, which means COVID-19, the normal, and the general pneumonia. And another task was to solve the 5-class problem, where we introduce a difference between bacterial and viral pneumonia. COVID-19 is a particular type of viral pneumonia that belongs to the coronavirus, as we have seen together with the SARS and MERS. And then we have also long opacity pneumonia, which makes this 5-class problem a little bit more complicated. So here we have the taxonomy, so lung opacity, bacterial, coronavirus, and the viral. what we did is to grab images from internet and making a data set of, for example, 404 images of each of them, of each of these classes. And we propose to this data set to the community by augmenting the data set to up to 4,848. We provided also the validation set with 100 images for each of them, and we provided the test set that we took from the hospital of Tolga in Algeria. 207 images for each of these classes. So just to make the problem a little bit complex, because the test images were from a different site, different acquisition system. The best, we tried several training possibilities with several architectures. In the end, what we have found is that using this architectures, training each of them independently, and then putting all together in an ensemble architecture like this one that you see in the slide, will improve by, let's say, 2 or 3% the performance as opposed to use just a single of this CNR. But this is a well-known result. What we did is to provide a baseline result for the 3 classes, reaching, for example, the F1 score, the overall F1 score 75%. In this particular experiment, the 207 images that have been used from the hospital of Tolga as a test, they were totally correctly classified. There was just difficulties in discriminating between normal and pneumonia. This is for the 3-class problem, and here we have a 5-class result with an F1 score a little bit improved to 81%. Then what we did is it the network effectively looking at the infection in the lungs? So we used one of the techniques that came in the scientific sector, which is the randomized input sampling for explanation, where we can see by the heat map how the information flows, so which neurons are activated. And in fact, for example, the red color means very high activation, blue is very low activation. And as we can see here, for example, for the normal, there is no red in the lungs. For the bacterial, we have here the spot that the network is looking at. For the COVID, we have these 3 spots in the lung, in the 2 lobes, and so on for the lung opacity and the viral. So we demonstrated that effectively the network was looking at the correct position of the disease in the lung. So, as I said, since the state of the art of the works presented in the state of the art at the time, I had no unified data, classes and evaluation protocol. It was hard to compare between other methods. So we did the comparison just at number of class level, the number of COVID, and also by considering the number of COVID-19 samples, and the accuracy achieved by colleagues in the literature. And of course, as you can see here from this table, there were very few examples with a small amount of COVID-19 samples. For example, the first one, they had only 25 images and 25 just for testing, and so on for the other. And we proposed these two data sets, one for 3 classes and the other for 5 classes, with this number of images, and the result that we the accuracy of COVID-19, of recognizing COVID-19, 100% for the 3 classes and 98% for the other, but the F1 score was much more lower because the network was not able to distinguish between, for example, the bacterial with the normal class, or the lung opacity with the normal class. And we provided the data set in GitHub and Kaggle, and published this on these results on sensors. But nowadays there are many data sets. Some of them are very interesting because they had a very huge number of scans, 21,000. This is for X-ray. And for example, this has been the first one has been proposed by Qatar University. There is another one, 29,000, the National COVID-19 Chest Image Database, and others have been proposed in literature. This is only for X-ray. So the work on X-ray was concluded at that time, and we started working on a much more informative image content, which is the computer tomography, the CT scan. CT scans are very informative. It's a very informative screening tool. It can be used for solving different tasks. For example, detection of COVID-19, the segmentation, the prediction of the severity, and the infection percentage estimation of the COVID-19. The last one is the one that we proposed in literature, which is much more complex, because the infection percentage estimation is to predict a number between 0 and 100, and the severity prediction, it's just to predict 4 or 5 group of severity. Infection segmentation is very important to recognize the infection and following up the patient states. However, developing a machine learning, an efficient machine learning approach to segment the infection is very challenging. Why? Because you need to have an expert that has to annotate manually the scan. And here we don't have just a single image. Here we have a certain number of slices. The computer tomography gets is a volume of information. That means we have several slices, and the expert must analyze and annotate each single slide. Other works, other tasks, for example, are related to the use of CT scans to predict the ICU admission, the intubation, and the percentage of mortality. So the main challenge, as I said, is segmenting the COVID-19 infections. And we usually do not have we don't have the access, the easy access to datasets of annotated data, especially if we want to train the deep learning models, which requires a huge level of data for the supervised training procedure. Also, the infection has a very high variability in intensity, in shape, in position, and type, which makes the segmentation task very, very challenging. The COVID-19 infection stage can be divided into early or advanced stage, and also there is a difference in appearance if it is with symptoms or no symptomatic, and the severity are additional factors that complicate the segmentation task. In more details, the infection usually appears as ground glass opacification, especially in the early stage. And the ground glass opacification is defined as an area of increased attenuation in computer tomography, of course, and then results in blurred edges and low contrast with the surrounding lung tissues. In later stages, the infection usually appears as a mixture of ground glass opacification and deconsolidation. And in this later stage, the infection segmentation is very, very hard. And this can be also hard for an expert radiologist. So in literature, two tasks are addressed for segmentation, let's say binary decision, binary segmentation, which is quantitative segmentation that shows how much the infection is spread in the lungs. And on the other hand, multi-class segmentation provides information not only about the degree of the infection spread, but gives also a better idea about the stage, the progress, and severity of the infection. So we participated to this grand challenge contest at the international conference at ICASP, the International Conference on Acoustic Speech and Signal Processing, where they provided us the dataset that contained 171 patients positive for COVID-19, 60 community-acquired pneumonia, and 76 as normal cases. But a number, a subset of these CT scans were labeled at the slice level. So only 55 for COVID, 25 for CAP, and only for them were each slice has a 0 if there is no COVID or no CAP, and 1 if there is COVID or CAP. So very small amount of them. That made the things a little bit complicated. The remaining was just the label, the unique label associated to the volume to each of the CT scan. So the first thing that we did, and it's very important, is the lung segmentation. At the beginning of our work, we tried classical image processing method, for example, marker-based watershed segmentation, where one marker is the internal marker identifies the lung tissue, and the external marker identifies the outside of the region of interest. Internal marker is obtained by thresholding the image and removing all the regions and leaving just the biggest one, because the internal is the much more darker. And the external marker is created by morphological dilation of the internal marker with two different iterations and subtracting the results. So in the end, we have these results that you see here in the third column, and this is a technique that is pretty much conventional, and it can be found also on Taggalo. Then we proposed an architecture like this that has a multitask strategy, so predicting the normal, the COVID-19, and the CAP for the CT scan. So we applied the two-stage architecture. In the first stage, we trained each of these architecture that you see to detect at the slice level the class, if it's normal, if it's COVID-19, or if it's CAP. So at the time, with this data set, we had just a very few number of CT scans related to each one of them. 30, for example, 30 for COVID-19, 55 for 30 for normal, 55 for COVID, and just 24 for CAP. So very small amount for CAP, and a very small number of them for validation, 9 for the normal, 17 for the COVID, and just 8 for the CAP class. In the second stage, we predicted the slice label for the whole CT scan using the trained CNN architectures. And since the number of slices of the CT scans varies from one CT scan to another, we propose dividing the slices into 20 equal groups, because we had CT scans with 45 slices, other with 100 slices, other with 80 slices. So we just divided them into 20 equal groups. For each group, we calculated the slice prediction percentage of each class, and concatenating them, concatenating the percentages of all CT scan groups, so we created the feature vector that we gave an input to the XGBoost classifier to predict the final scores for the three classes. As you can see here, there is a preprocessing stage, and this is because the CNN architectures usually are trained with ImageNet or other dataset that you make use of RGB images, but the slice is just one plane. So we stacked the gray level images with this kind of information by building this volume by taking the original image, multiplied the binary mask, and getting the segmentation results and the original image. So in the end, we have the stacked results, which is the three of these planes altogether that are useful that are being provided in input to each of the CNN architectures. So to train these models, we made some dataset augmentation, and we ended up with a number of slices like this, where, as you can see, this cap is very unbalanced. In general, the three classes are very unbalanced. And so we did this data augmentation in order to try to balance a little bit with this kind of transformations, which is much more mostly common in this context. So the stage one is a slice level classification. So once we have the pre-processing, we build the stack, the three planes, which we give to the one of the CNN. And in the end, we have a fully connected layer where we grab the features from this. But we added two extra information, which is the slice location. We divided the volume, the CT scan volume, in 5 regions. So the first region, for example, is the one close to the neck, and the fifth region is the one close to the stomach. So we considered the position of the slice into these 5 regions of the lungs. We also added the total number of slices, and we used this feature vector that is connected to these 2 branches. The top branch is related to discriminate to score for normal, COVID-19, and CAP class, and the second one was to predict which position in one of the 5 regions is the slice. So in the end, we achieved reasonably acceptable performances. Here is a slice level classification for each CNN backbone with some training details. I will skip this. And the general architecture that is composed from the first stage, the slice the single slice classification, the second stage where we concatenate the feature from each CNN backbone and provide an input to XGBoost, we arrive to reach 87.75% accuracy, which was a good result for the challenge. Here we can see the heat map with the RAISE method for the explainable AI in order to see where is looking each one of the CNN architecture that we have investigated, that we have trained. So as you can see here, the input it's a COVID located in the 2 red rectangles, and the red spot is where the network is paying attention. An extended version of this work has been also published on Sensor. So in the end, we scored 5th, but we were the first in sensitivity of COVID-19. One of the problems that we had is the small amount of CAP. We didn't found a good way to improve with a small number of available data for the CAP class. Then we proposed our own dataset, making things a little bit complex, not classifying just the COVID-19, but providing the percentage of the presence of the virus into the lung. The COVID infection percentage estimation was computed in the slides just as 100 multiplied the number of pixels considered the infection and the number of the total pixels that are related to the lung. So there was an annotation procedure that had to annotate the lung, and the expert had to make the boundary of the COVID infection. Usually, let's say that it is considered normal if there is no infection, of course, minimal if the percentage of the presence is below 10%, moderate between 10 and 25, and so on. And this is done, of course, for each slice, and we made publicly available this data set and published on Journal of Imaging. In order to segment automatically the lung, there are some data sets that can be used. So in this case, you can train a model to segment the lung, and the radiologist has only to annotate the infected portion of the slice. We also proposed a data set for this with 183 CT scans and 3,986 labeled slices for the infection percentage, which were annotated, estimated by two radiologists. But we took only the slices that were in agreement between the two radiologists. So if there was a slice in disagreement, that slice was thrown away. We took the 150 CT scans from one hospital in Algeria, and the other from Tolga, another hospital in Algeria, 33. These CT scans were acquired from different acquisition instruments, and we can see we have a bigger number of patients with a small percentage of presence of virus, and just the severe was very low as a number of examples. And here you can see the number of slices for each CT scans that varies, and they are related with the CT scans acquired, and also the one in agreement with the two radiologists. So we introduced the loss function as mean square error, the Huber, which is less sensitive to outliers, and the evaluation matrix was made at slice level, so the mean absolute error, which is the percentage predicted minus the sum over all slices and of the predicted estimated y hat I percentage with respect to the ground truth y sub I, and also the root mean square error and the Pearson correlation coefficient. We did these three metrics for the slice level and also for the subject level. Okay, in the end, we proposed the baseline, which is this one, by providing a different folding, different folders, so five-fold cross-validation, and we asked to the community to join this challenge, which was presented at the international at a workshop named MIA COVID 2022 medical imaging analysis for COVID 2022, and it was presented at the International Conference on Image Analysis and Processing that we organized in Lecce. We evaluated the score of each of the teams with respect to the mean absolute error, the RMSE and the PC, by weighting the two different results. The results that they got in validation, just 30% of the score was considered, and 70% for the results that they scored in the testing phase. We had 40 teams, around 40 teams that's registered, but in the end, only 6 of them were better than the baseline, and we only considered the 6 of them. So as you can see, the mean absolute error, it's very interesting. That means that it is able to estimate the percentage of the presence of the virus into the lung with an error of around less than 4% for the best team, 3.84. But of course, there is more space to improve. If we consider the minimal case, here the ground truth was the black line. Let's say that four of the teams were much more close to the ground truth, and especially you can consider the x-axis that goes from 0 to 45, 43 slices. So the left part is the one close to the neck, and the right part close to the stomach. So in the middle, there was a little bit of error, but just a small number of errors. And here for the extent case where the presence of virus was important in the end, for example. And here for the severe case where almost all the teams made some introduced much more error at the beginning and in the end of the volume, and this is because of the small number of slices, small number of samples related to the severe case. What is the procedure that all of them have used? Well, what are the features of the proposition of the teams that participated and won For example, we analyze the preprocessing technique, the backbone that they use, the kind of architecture, the loss function they use, if they use deep features or not, if they use the pre-trained architecture or not, if they use the ensemble, or if they make use of the data augmentation. What we have noticed that none of them, for example, especially the first three places, they didn't make use of pre-processing. But the nicest thing is that, let's say that the first two were the one that make use of transformers. The first strongly used transformer. Transformer, as we know, is a technique that is scoring very important results in computer vision. And the second team, they made use of the standard convolutional network architectures, but they after the use of the CNN, they introduce a self-attention mechanism, which is at the base of the transformer. And this means that today transformer is gaining also very interesting results in this context. So going to the next architecture that we have introduced, because we didn't participate to the challenge, of course, because we were the organization that proposed this challenge, but we proposed a technique that is related to this COVID segmentation. We named ILC Unit++. As an architecture for the segmentation, usually for semantic segmentation, usually the unit, which is an architecture that is U-shaped. As you can see here, the black one, the black lines and circles are the standard unit. It is composed of an encoder. Then we have, for example, here in X40, the last convolutional transformation. We have the latent space where the information is smaller. So along this backbone, we have convolution and subsampling in order to have smaller information. So the encoding part, and then the upsampling on the decoding part in order to finally have the segmented mask of in this case of the infection. We experimented what is named the Unit++, because the Unit++, as you can see, has this green and blue skip connections, and this has been introduced just to bridge the gap, the semantic gap between, for example, the X10 convolution and what is reconstructed on the decoding part. Some of the small details, for example, may get lost along the encoding, the decoding, if we follow the unit, the standard unit architecture. But with these skip connections, things are much more improved. So we made use of this architecture, the Unit++, and we made this modification in the decoding stage, just introducing two decoding branches. One is related to the reconstruction of the lung, and the other is related to the infection segmentation. So we reconstructed. We wanted to solve two different problems. One is for the segmentation of the lung, and the other is for the segmentation of the infection. Here are some results by using two datasets. So as you can see, the first row on the left is the input slice. Then the second row on the left is the ground truth. And here are the various architecture, the results of the various architectures starting from the unit, detection unit. It's another variation of the unit with the self-attention mechanisms, the unit plus, and our proposed architecture with the results of the two data sets that we have been using, which are publicly available. One is a medical segmentation for COVID-19, and the other is provided by Zenodo. We experimented the results of this ILC unit plus by using just dataset one dataset, for example, for training and validation, with reasonably good results, 74% of F1 score in one case, 70% for the other. And the other results was to consider one dataset for training and the other for testing. And the results were a little bit lower, but still better than the other. Of course, being segmentation problem, we computed also the dice score, the intersection of over union, and the usual sensitivity, specificity, and precision. So we use this architecture to participate to the second COVID competition that we presented yesterday, the results at ISASI board. This year is in Tel Aviv. And we participated to two different task problems. One is related to the detection. So the model had to recognize COVID or non-COVID. And the other is the COVID severity detection. So as you can see here, is not percentage estimation, but it's a, let's say, different task where we had to discriminate between mild, moderate, severe, and critical from the CT scans. The data set that we had for the detection were for example, this numerosity, 882 for COVID for training, and more than 1,000 for non-COVID, and validation to more than 200. And a small amount on numbers of CT scans for the mild, moderate, and the critical, for example, just 26 for training and just 5 for validation. What kind of architecture we have proposed? So first of all, we introduced the slice removal stage as a pre-processing where we trained the ResNext 50 to detect lung or non-lung as a slice classification. So we removed the slices that where the lung was not in there. And we resized the results, and in order to exploit the power of the CNN architectures, we introduced the hybrid dense architecture. So the proposed hybrid dense architecture consists of two elements. One is a convolution block with a 3x3 kernel, which transforms the 64 input channels to 3 channels, just to provide an input to the classical architecture. And the second component is DenseNet 161 that is pre-trained on ImageNet. And finally, in order to boost the performance, we considered an ensemble approach in order to average the prediction probabilities of the 3 hybrid dense architecture models, which have been trained separately, the same model, but trained in a separate way, for the detection of COVID-19 detection. This is the architecture for the COVID-19 detection. As you can see in the output, we have just the two scores. For the severity, we have as you can see here in the input, after removing the non-long slice and the resizing, we divided the volume into different sub-volumes, 32 and 16 slices, just to have 2 different point of view of the CT scans, and they were given an input to this conv layer, which is a convolution like this. So the first volume had 219 by 219 by 32 channels, provided in input to a conv layer that is composed of 3 convolution of 3 by 3. This is a little bit confusing, but anyway, the convolution had 3 filters. Each filter is has a dimension of 3 by 3 by 32, because 32 was the depth of the input volume, the padding of 1 and stride of 1, in order to keep the spatial extent of 219 by 219 to provide an input to the next stage, and then the second portion of the volume, also this one was provided to another the same convolution with other 3 filters, the nonlinear activations. So they were concatenated the results, providing 6 activation maps of 219 by 219, and they were provided to another convolution just to provide an input 3 activation maps, because the standard CNN architecture, for example, inception with V3, V4, and the other inception ResNet, they were trained with ImageNet, and they have an input. They require an input 3 channels. So as a result, the probability that there has been a probability means the argmax, in order to provide the 4 different classes. So we provided several results, but the ensemble was the one that provided the best results for this is for the detection of COVID or non-COVID, where we scored 5th in the rank, and for the detection of the severity, so the 4 different classes, we had the best results with the ensemble model, and we scored 3rd in the challenge that we have participated at the ECCP workshop. So we went much more. If we consider the F1 score for the baseline, from 40 to 47%, and we have these results for the mild, the moderate, the severe, and the critical, as an accuracy score, which is very low, and this means that the task is very challenging. The last architecture that I just wanted to introduce is the use of transformer, which has been just submitted. It makes use as you can see here, we have the original the input slice, which is provided to an encoder, but we also split the image in patches, and these patches are provided to the transformer. As you may know, transformers is able to get richer information, especially for discovering long-term interaction for time series, or in this case, discovering the position embedding. That means discovers the position of some details into the image. If there are two particular appearance information that occur in two specific areas of the image you are analyzing, the architecture pays much more attention to those parts and remember that information for the representation of the input image. And this is the division, considering small patches, the small areas of the image allows to represent local interactions between these patches. And by providing the entire image, allows to remember global information. So the local information is useful to avoid discarding small details with respect to the entire image. So the task here was, the architecture was an autoencoder, and the task was to detect the infection and the lung. So we required to segment two different information. I will not go into the detail of the architecture, but it's a U-shaped architecture where this part is the encoder, where global information is concatenated with local information from the transformer, and in the end we will have the upsampling part, which includes self-attention mechanisms, one branch to reconstruct the infection, and the other branch to reconstruct the lung. And the results that we obtained was the best results that we scored with our research activity in this context. Here we, on the first column, is the slice, and we have the attention unit plus, and all the other architecture that are leading state-of-the-art, the ScotNet and AlarmNet. And our proposition, we named it with a very bad name, the TRAT unit, has the best performance with respect to the ground truth in the last column. This is for the binary segmentation, and here it's a multi-class segmentation where we have the infection of the lung and the background with the infection highlighted in red. So to conclude, key aspects to consider in this context. First, ethical and legal questions. Do patients own their identified data? What is the method, for example, to re-identify data? What if the method, if methods to identify data improve over time? Should the community make open source large quantities of this kind of data, because we are grabbing even if in an anonymous way, we are grabbing personal information, and in order to publish a paper, we need to have an ethical committee that must be activated, and only after that the procedure to make the study can be published. And also there are some aspects that may work around the stricter jurisdiction. For example, in Europe, we have the GDPR, which is a barrier with respect to some aspects, especially in the health sector. But for example, federated learning can be a solution in which a centralized algorithm can be trained on distributed data that never leaves protected enclosures. Another issue is the use of not only images, but also to have access to text data. We have a multimodal information that may improve the diagnosis. But here we have the barrier of having the electronic health record, where the information related to the patient is in there, and privacy issues cannot allow to disclose this kind of information in an easy way. Let me jump to the conclusion. So let's say that these techniques have been shown very promising results. They have shown that the quality of the diagnosis improve if the doctor make use of an artificial intelligence system, and let's say that it equalizes the treatment to the public, because a novice doctor can make use of the expert system in order to try to provide a precise diagnosis. Obviously, the super expert doesn't need the super expert doctor doesn't need this kind of technology, but it can be useful for the novice and the middle experienced doctor to improve the quality of the diagnosis. Critical aspect is in the health sector to have large quantities of data or annotated data, because the experts usually do not have time to annotate them, and we cannot use the same annotation done with the standard dataset, imaginary dataset, by using the Mechanical Turk, the Amazon Mechanical Turk system, because we need experts to annotate the image. The presence of unbalanced classes poses critical issues in the training phase. And as I said, last slide, the convergence between metadata may improve the decision process, and also privacy issues are things that must be addressed in the near future. Here is the small team with which we have done this this research activity. My collaborator Fares Bogorzi, Professor Talagomed from University of Valenciennes, Professor Faiz Naika from the Basque University in Spain, and Professor Abdul Hadid from the Sorbonne University in Abu Dhabi. Thank you very much for your attention. I hope you enjoyed this talk.
Okay, Claude, thank you so much for your presentation. Now we'll open to some questions.
Let me.
Thank you. Thank you for can you hear me? Can you hear me?
Hi, leader.
I know that there is some delay, right?
Yes, I hear you now.
The question is, in your experience, do you see any advantages in processing these 3D images, like CT images of the lab, using the slice approach, like 3D approach, or 2.5D or 3D approach, for example, in the networks? Do you see any, or have you tried to evaluate there is any difference, for example, when you do the segmentation of the ground glass, let's say, you could do that segmentation in 2D or in 3D or in 2.5D. So do you see any advantage or disadvantage in taking of these approaches?
So if the segmentation can be done by using the 3D volume instead of using just the single slice, is this the question?
Exactly. If you see any in doing one way over the other, for example.
In our case, there was no. In our case, we worked with slices that in the middle was not considered. For example, slices that did not that the two radiologists did not agree with their decision. They were the slices in that case were thrown away. So we lose that kind of information, and it was not possible. In that case, it is not possible to work with the volume because some of the slices are thrown away. But probably if we keep all the slices, the segmentation, instead of considering the 2D, but the 3D can be for sure very informative, very useful. But we didn't work with the 3D volume for the segmentation at the moment. Also because mainly the problem of segmenting the lung was mainly in the plane done. So, but probably in the future could be very interesting activity to do.
I can foresee that it might be more difficult to build backbones that are deep if you work in 3D because of the memory, right? You're going to have more memory demand as compared to 2D. But I'm not sure, for example, for segmentation, do you really need deep neural networks, a deep backbone? Or if the backbone is shallow, it solve the problem as well, for example.
Let's say that we did work with 3D information in input to the backbone. At the moment, what I didn't like, but we had to do that, and we reached quite good performance, is that when you have an input volume that is different, because as I said during the talk, the standard CNN nowadays, they use RGB images. So mainly we had to give to them three planes, okay? As you have seen, what we have done is to include convolutional layers in order to reduce the number of channels. That kind of, it is usually done in that way, when you have an input which differ from the standard working procedure of the standard backbone. But probably what we haven't done is to cut the first convolutional layer and provide directly without reducing the information, reducing the number of channels, providing directly the volume. In our case was 299 by 299 by 64, for example, because we had the 64 slices. For memory demanding is not a problem, because we usually have a large number. The Titan RTX, I guess it has 25 gigabytes of memory. So training the single architecture is okay with a batch size, if I remember well, was about six volumes. So was not that problem. But for sure, reducing the number of reducing the volume in that way, it's a kind of information loss that is involved in the performance of the architecture may decrease. But we didn't have time to experience other kind of stuff. But anyway, the use of ensemble, in our case, the ensemble is not trained in an entire way, but the training was just with a single architecture, and then in the end, we put all together just as an inference.
Thank you.
No more questions? Lunchtime here. Lunchtime. Cosimo, thank you so much. We will close now the session. If you want to say something.
It's been a pleasure, and I'm very sorry not being there, because I'd love to come visit you. And anyway, thank you, Luis, for the nice invitation. Thank you, and Douglas, for the nice introduction. And I wish all the best for and the success of the Sibgrapi conference.
We should thank you very much, Mim, for being part of the program and for giving the talk now. Thank you very much. And
thank you. Thank you. Bye-bye. Bye.
tem ainda lá no Nau, como é que está? Pode pegar os vouchers.